Welcome to lecture number 34 of the Statistical Thermodynamics course. So previously we saw that how the complex model seems to address some of the combined effects of, if you look at it here, vibrational and harmonicity, rotational, centrifugal stretching, okay, and of course the rotation vibration coupling. So these were the three things that the complex model seems to incorporate. So this is what constitutes the complex model that we did in the previous lecture, right? In comparison to the simplex model, which assumed an harmonic oscillator and a rigid rotor. So pursuing this avenue, so the total Ro-vibrational energy within given electronic state becomes ERV equal to GV FVJ. Okay, this is the total rho vibrational energy. So if we expand now this GV and FBJ, so it will be omega E V plus half minus omega E XE V plus half whole square plus, these were the correction terms if you recall, J into J plus 1 minus DE J square into J plus 1 whole square. Okay, so this is the total rho vibrational energy for any given electronic state. Now, furthermore, for an harmonic oscillator, okay, the vibrational selection rule, okay, is no longer okay, limited to our previous analysis, which showed that V will be equal, delta V will be plus minus 1. In fact, we should now have some revised selection rules. So the revised selection rules are okay, for the complex model. This model will be V prime minus V double prime, V1, 2, 3, J prime and J double prime will be equal to plus minus 1. Okay, so that V double prime equal to 0, then V prime minus V double prime equal to 1. This designates fundamental transition. Okay. On the other hand, V prime minus V double prime is equal to 2. This designates the first overtone. Okay, and V prime minus V double prime equal to 3 designates the second overtone. Okay, got it. So now So you can see that okay, these are, so one is a fundamental transition. These are what we call the first and the second overtones for V double prime is equal to 0. Now, for V double prime greater than 0, the Ro-vibrational spectra, the Ro-vibrational spectra corresponding to V prime minus V double prime equal to 1, 2, 3. Okay, would identify by the various hot bands. We designate the various hot bands. Okay. In general, so why they are called hot bands, we will come a little later. In general, higher overtones become progressively weaker by about factor of 10, one order, factor of 10 in comparison to fundamental transition. Okay. As the name implies, these are called hot bands because they only appear at high temperature. These bands only appear at higher temperatures. Okay, when there is significant population is generated. When upper vibrational bands, the upper vibrational bands, okay, sufficient population. Okay, all right. Okay. So for the simplicity, we can also neglect the rotational centrifugal stretching because this complication is often minor in comparison to the remaining contributions. So therefore, the wave numbers in any Ro-vibrational spectrum, the wave numbers in Ro-vibrational spectrum, okay, this is assumed neglecting rotational centrifuging, rotational centrifugal stretching. Stretching is delta RV is equal to WE V prime minus V double prime minus omega E XC plus 1 minus V double prime plus 1, okay, plus EV prime J plus 1 minus DV double prime J double prime plus J double prime plus 1. Okay, so that transitions, for those transitions which are associated with V prime equal to 0, that means ground, or let us write it formally, transitions affiliated with ground vibrational level, which is V double prime is equal to 0, therefore becomes This is for the P branch. Minus P prime plus P prime J double prime plus where your J double prime equal to 1, 2, 3, da, da, da. Similarly for the R branch, VR is equal to AV plus 2B prime plus B prime minus double prime J double prime plus EV prime double prime J double prime square. Okay, where J double prime equal to 0, 1, 2, da, da, da. Okay. So for the P branch, J prime is equal to J double prime minus 1. The R branch, okay, J prime is equal to J double prime plus 1. Respectively. So you can see that if you compare it with the simplex model, the rotational energy is either added or subtracted from a pure vibrational contribution. Okay, specified in this case. Okay, so on the basis of this, the line spacing for Ro-vibrational spectroscopy. So we must be this is the line spacing for the P branch. And for the R branch, P this is for the P branch and this is for the R branch. Okay. Now, since alpha E is much less than BE, okay, we can conclude, we can show that PV double prime is greater than equal to PV prime if your BV double prime is equal to BV prime. Okay, this basically replicates the simplex model. Okay, if on the other hand BV double prime is greater than BV prime, the case, then this actually says that the spacing between consecutive lines in P branch grows with increasing J double prime. Okay. Also, from the second expression, if you look at this now, this will imply that the spacing between consecutive lines in R branch drops with increasing J double prime. So this is actually explains the HBR spectrum quite well. This explains the HBR spectrum that we drew earlier. Okay, spectrum. By using on these square fits, we can actually the infrared spectrum, as we know that it is infrared dominant. We can determine various spectral parameters like omega E, XE, E, and alpha E. So all these can be determined by just doing on this square fit. Okay. So, but this explains the spectrum. This is a model in which you can actually, this model, remember, comes from the Morse potential by a power series expansion of the Morse potential. We have skipped the math, but these are the selection rules which now actually says that what the P branches and the R branches of this particular series is all about. So, so this takes us, so now you can do sample problems which are also given in the book. So that we will cover in the tutorial part of this particular lecture. We will move on to something which is called electronic spectroscopy. Now, this is a little bit more complicated because now we have simultaneous changes in electronic, vibrational, and rotational energy modes. We have simultaneous changes in electronic, vibrational, and rotational energy modes. Okay, so now we will call this Ro-vibronic spectrum. So Ro-vibronic spectrum. Okay, so for the Ro-vibronic spectrum, the change in internal energy is therefore given as delta TE plus delta GV delta FJ. So the three terms present represent the variation in the electronic, vibrational, and the rotational energies respectively. Now the shift in vibrational energy now depends both on the lower and the upper electronic energy levels. The same applies to the rotational energy also. This depends, moreover, this change depends on both the lower and the upper vibrational energy levels. In addition, because you have this transition dipole moment controlling the Ro-vibrational transitions, even for symmetric molecules like oxygen and nitrogen, you have electronic spectra. So now we consider for simplicity, okay, for simplicity, the ground and the excited electronic states of a diatomic molecule. Ground and electronic energy states of a diatomic molecule. That can be written as J. Okay, so the ground and excited electronic states of a simple diatomic molecule, okay, where the band origin is defined as okay, is defined as this. The band origin is dominated by about E, which is the order of 10 to the power of 4 to 10 to the power of 5 centimeter inverse. This corresponds to visible or UV part of the spectrum. Okay, so therefore the vibrational contribution or delta GV vibrational contribution can be written as omega E prime is half square minus omega E double prime plus half. So omega E double prime x double prime E double prime plus half square. This, where the single and the double primes refers to the spectral parameters affiliated with the upper and the lower electronic states respectively. The upper double prime is the lower electronic states respectively. Okay, so this refers to the upper and the lower electronic states. Analogous to the the Ro-vibrational transitions now. Okay, the selection rule, the vibrational selection rule or Ro-vibronic vibrational selection rules for Ro-vibronic transitions delta equal to 0 plus minus 1 plus minus 2 plus minus 3 data. So any vibrational level in an upper electronic state can be linked with any vibrational level in the ground electronic state. Okay, so any vibrational level in the upper, that's why you have the 0 plus minus 1 and plus minus 2, etc. So any vibrational level, okay, in upper electronic state can be linked, okay, with any vibrational level in ground electronic state. In particular, an electronic spectrum containing vibrational bands with constant delta V is called a sequence. Okay, and a spectrum containing regular vibrational bands with either constant V prime or V double prime is called a progression. It's called a progression, and the other one is called a. So just to make sure that what we call that any electronic spectrum containing vibrational bands, okay, with constant delta V, okay, is called sequence. Okay, a spectrum containing regular vibrational bands, and spectrum containing regular vibrational bands, okay, with either constant V prime or V double prime is called progression. Okay, so such sequences and the progressions are best understood if we use an energy level diagram, which we will do in the next class, right? But so the Ro-vibrational we can write down to the rotational contribution as, before we draw the diagram, the rotational contribution as delta FBJ is equal to prime J prime J plus 1 minus D prime J double prime square minus square. Again, the double prime and the single prime refers to the upper and the lower electronic states respectively. In comparison to the Ro-vibrational case, the rotational selection rules are delta J 0 plus minus 1. Okay, so we now entertain the possibility of a Q branch also. So there could be a possibility for a Q branch, okay, which is basically delta J equal to 0 is possible in addition to R and E branches. So we'll discuss more of this in the next class, where we'll also draw the the energy level diagram also to explain sequence and progression in more details. So let us stop here. In the next class, we'll pick it up from here.